in, everyone. Come on in, everyone. I'm finishing up some stuff real quick, and as soon as I see everybody's about here, I'll go ahead and start up. Another one coming in. All right, it looks like we got 6 of you. That's not really enough, but I guess we should go ahead and get started. Does anybody have any questions before we get started? Now, remember, during class, you're welcome to just shout out that you have a question or something like that. You don't have to. You can type it in the chat if you don't have, for instance, a speaker or a speaker that works. But you can also just speak it up if you have a speaker that works. Same thing now. If you have any questions, ask me. Also, in general, I often forget to ask you guys just because I'm so excited about the material I'm covering. I'll just jump right in it and start teaching and completely forget to take questions for any homework problems or any past material. But the beginning of every class should start with 5 to 10 minutes possible of time where you could ask questions about homeworks. Far as I know, your mastering physics is working, but I did just discover that evidently the syllabus that I posted last night, or excuse me, the night before last, it didn't get posted. So I don't know what happened. I don't know if I lost internet connection or whatever, but I will post that tonight. It should be available sometime tonight or first thing tomorrow. And just like Tuesday, I did put the video up the same night. So hopefully I should be able to get it all converted, downloaded, and re-uploaded with by say 10 o'clock tonight, midnight tonight, or something like that. If not, it'll definitely appear the next day. And remember, the terminology that I'm using is generally like this video will be called, when I go to upload it, this video will be called, I'm going to type it right here in the text, I mean in the chat. So this is what the video is going to be called. Tonight. That does not mean that will not be the title of the video when it gets onto YouTube. But if you look down in the description box, you will see an actual that string of letters. It normally cuts out the underscores and other symbols, so you should see that. You should see that in the description. And the reason why I'm telling you that is because whenever you find a video that you like on my YouTube channel, it should have a marker like that in the description, and that's the name of the file that is represented by the actual notes that I took. So even back when I was taking them on paper, I made a point to take a photograph of the actual written notes and then put them all in a PDF and posted them to my Google Docs. And that would be the title of the Google Docs. So basically, it's always going to be like a PHY for physics or a NAS for astronomy. Then it'll have the course number, 130, 131, 132 for physics, for astronomy, or 201, 202, 241, 242 for physics. And then it'll have the section number. In this case, it's N01C because that's obviously the section for our class out of Chesapeake. Now, it'll also have the date, as you see right there, 05/23/2024. All of that's plenty enough information for you to be able to find exactly what you need, but it will always be on there. So make sure you know that. And remember that if you look up in the important links and documents, you'll find a link to my YouTube channel, or excuse me, not only to my YouTube channel, but to my Google Docs, where you're automatically allowed to just download it from there. So So I'll ask one more time. Anybody have any questions before we get started? You can ask me questions about past homework. Since the syllabus didn't get posted, you might have some questions about how this class works. So I apologize for that again, but I can tell you that off the top of my head. So if you have any questions about that, that's fine. I did make the homeworks where they're not due until the 29th. So that should be for you guys, that'll be Wednesday night at 11:59 p.m. So your homework for chapter 17 should be due Wednesday night at 11:59 p.m. We probably are not even going to get to chapter 18 tonight, so that will probably be moved back as well. I think it's currently listed as the 29th, but I'm probably not going to do that. And we'll catch up a little later on that. Sometimes I can use some of our lab meeting sessions, but with your class, you don't get to meet me in lab, you meet someone else, so might not be able to do that there. I will talk to Miss Raskovic, and if she has certain nights that we've slated for other things, I might usurp that position a little bit and do maybe a 1 hour session to try to catch up from here every now and again. But I'm not positive about that. So just pay attention, and I'll talk to Miss Raskovic about that. So again, one more time, any questions? Okay. Well, I will tell you the best way to do physics is to do physics every day. So literally, if it's just a unit conversion problem that's not even a physics problem that was in your homework or was in your book. It might be something as simple as, hey, let's calculate how much oil I should put in a gas tank that is a 5 gallon gas tank, and you can assume it has 5 gallons of gas in it. If I'm doing it for a weed eater that takes a gas to oil ratio of 40 to 1. How about for 50 to 1? So that's two problems you can do anytime. I highly recommend literally every day, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, you do a physics problem. And that could be, like I said, something as simple as converting units or kinematics stuff that you learned from the 241 class, or in here, of course, you could do some ideal gas laws. Hey, what is the volume of air at standard temperature and pressure, that kind of stuff. And that would require you, of course, to understand that air is about 80% nitrogen and 20% oxygen. And then from that, you can get roughly a number of moles for a certain number of grams, that kind of thing. So all right, looks like no one's typing any questions, so I'm going to go ahead and move along. When we last spoke, we talked about in chapter 17, we talked about units, system of units with regards to temperature. Specifically, we talked about the Celsius and its cousin, the Kelvin scale. And we also talked about the Fahrenheit and its cousin, the Rankine scale. I will tell you, it is absolutely within the norm for me to ask you to convert a Celsius temperature to a Fahrenheit temperature, or a Fahrenheit temperature to a Celsius, or even a Fahrenheit to a Kelvin, or even a Celsius to a Kelvin. So I've given you a nice, pedagogically reasonable way to convert between Celsius and Fahrenheit and Celsius. And I highly, highly, highly recommend you do that on every problem you solve. That being said, in a test situation, I can't necessarily know what you're doing on that. So if you get panicked and you feel like, I've lost something, I don't understand this, you can go ahead and use the formula if you happen to have that formula memorized. Or if you don't happen to have that formula memorized, it literally takes like a whole minute to derive the formula, whether you're converting from Celsius to Fahrenheit or Fahrenheit to Celsius. So you can just derive that really quickly and then do the calculation. And the ideal scenario would be you do it like I taught you, with the pedagogically reasonable way, or the way that's supposed to be most beneficial to your learning. And then you could do it the regular way and make sure you get the right answer. But that's what I want to tell you. On a test, you do things a little differently. You don't necessarily show all your steps. And sometimes you show way more steps than you mean to, just because you want to work it out nicely. And sometimes you just don't do it the same way that you normally would in homework. So but that's basically what we did with the previous chapter. I also with this chapter 18 in the previous meeting, I also talked to you about thermoscope and converting a thermoscope to a thermometer, and talked about the various variables you could use for that. So for instance, you could use a fixed volume gas thermometer. What is a fixed volume gas thermometer? Well, if you could imagine, let's say a hollow aluminum sphere, and then the hollow aluminum sphere might be like this big, maybe it's got a diameter of 30 centimeters or something like that. That's a pretty good sized sphere. And then you'd have just a single little cylindrical pipe sticking out of a part of it that would go to a pressure to an actual pressure gauge. So you can actually read the pressure directly, and maybe you'll have a valve on it or something that you can open up to pump a certain gas in there and to pull out a certain gas or whatever. But in general, if you just kept it closed, it would have air in there, and that would be just fine. But the main thing is what you'd find out if you use that, if you actually basically measured some pressures for various temperatures, what you would discover, since the volume's being held constant and since the valve is actually closed, you also know that the number of moles, the number of atoms, or even the mass of the gas isn't changing. So literally the only thing that can change there is pressure and temperature. If you actually, submerge that bulb of aluminum with the gas inside of it, if you submerged it in a liquid that was at, let's say, 0 degrees Celsius, and you left it there to reach equilibrium, what would happen as it's reaching equilibrium is the pressure would likely, assuming it came from a hotter place, would likely go down, 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 and then it would slow down and come to a stop on some fixed amount of pressure, and you could write that pressure down for 0 degrees Celsius. Then you might do something to try to increase the temperature of that water from 0 degrees Celsius to, say, 10 degrees Celsius. And if you did that, you could then, once you held it down using an actual thermometer to make sure the temperature is 10 degrees Celsius, you could then stick the vat or the container back in the water again, wait for it to reach equilibrium, and record that for a volume. Now, if you ultimately did that with several pressures and temperature combinations, what you'd ultimately get is a ability to plot temperature versus pressure, or pressure versus temperature. Like you'd normally say, put the pressure on the vertical axis and the temperature on the horizontal, but you could also say temperature on the vertical and pressure on the horizontal. And what you get is essentially a linear line, a linear graph. And you could do that. And if you did that with air, you'd get one result. If you did that with hydrogen, you'd get a slightly different result. It would still be a straight line, but the straight line would have a different slope. It wouldn't lay exactly on the same spot. If you did it with helium, you'd get a different line. But the neat thing is, if you actually did that, you would get a graph for every element or compound we've ever tested. All of those graphs would all converge on a single specific temperature. And you couldn't get anywhere close to that temperature because the ideal gas law doesn't work that well at lower temperatures. And the lower the temperature you get, most gases will actually turn into a liquid and then ultimately into a solid. Not all of them. For instance, we have some difficulties with hydrogen and helium. They require a lot. But the big deal is they all would be a series of lines like this that had varying slopes, but all of them would converge on one point on the temperature axis. And what that would mean is that at a pressure equals zero, that's when you're on the temperature axis, at a pressure equals zero, they would have all the same temperature, and that temperature would be what we call absolute zero. That's why we call it absolute, and it's negative 273 degrees Celsius, essentially, or negative 492 degrees Fahrenheit. Would be the absolute zero as well. That negative 492 is called zero of Rankine, so that's zero Rankine temperature, and that negative 273 degrees Celsius is 0 Kelvin, and again, we don't put degrees on there. So that's why we have degrees on the temperatures, specifically because the use of water as the fundamental substance to make up a scale for temperature from 0 to 100 means from freezing to boiling, or from 32 to 212 from freezing to boiling in the case of Fahrenheit. That's why they have a degree mark on it, because that was somewhat arbitrary. We might meet an alien species from, maybe even an entirely different galaxy than our own, and they might not be so preoccupied with water. I find it kind of hard, but my knowledge of biology and biochem is not that great. But there might actually be life forms that don't require water. And if that's the case, then that life form probably would see our Fahrenheit and Celsius temperature scales as kind of quaint. But if they were advanced enough, they would certainly have something equivalent to the Kelvin scale and the Rankine scale, or at least one of those. Now, the angles, or the number of degrees between freezing and boiling of water would not be on there. But the main thing is they would all agree with us of what the absolute zero is. So that's what I mean about that. Anybody have any questions on that part? Let me pull over. I'm just going to refresh my memory and make sure I haven't left off anything regarding temperature and thermometers, temperature scales. I'm just looking quickly over the textbook. Yeah, we did talk about bimetallic strips to some extent. You should, if you have a chance, you should take the time to look at an old style. Actually, let me pull one up here. Let me see. Let's see if we get any cool pictures that would help me. I recently replaced my own thermostat at my home, and I found that it was really hard to find the old style. I ended up going with a digital one, and that's kind of a bummer where there's actually a lot of cool old ones that are very instructive from a physics standpoint. So I thought I'd just look for one of those real quick. Uh, I did a search for old thermostat type, and all I'm getting is pictures of fairly new ones and then pictures of ones that have the lid on, so it doesn't do me any good. Let me quickly go through here because I'd like to share one with you and show you what I'm talking about, but it looks like it's not coming up. If you were in my face-to-face class, I would actually have one that I could show you. Or what's this one? Nope, that doesn't have it. Oh, let me double check. Nope, that does not have it. Well, Reddit's no good to me. Okay, let's see. Sorry I'm taking this much time. It's not critical how much time I'm taking, but still, any time that I spend doing this instead of actually teaching you is suboptimal. I'm not seeing one. That's kind of a bummer. Okay, well, what I'll do is I'll draw one a little later. I've got some of the notes worked out already just for stuff. Oh, there's a good one. Let's see. Dang it, it's too small to see. Let's see. Maybe it's bigger in this other picture. Nope, it's crap. It's complete crap. It actually had it, but you can only see it from the side. You could barely see the coil of metal. Your textbook actually has a picture of one as well, but it's just of a coil, a bimetallic strip being used as a thermometer, not a bimetallic strip being used as a actual thermostat to tell your heat to turn on or your air conditioning to turn on. That would be the ideal thing to show you, but I'm just not seeing it. So, all right, I've wasted enough time on that. I will refer you to figure 17-6. That literally shows a bimetallic strip that's in a coil. And basically, what happens when the temperature gets low, one side of the coil, well, both sides of the bimetallic strip will actually get colder. And the deal is, since it's bimetallic, one metal will shrink less than the other side. The side that shrinks less will stay on the outside of the curve, and the side that shrinks the most will be on the, or excuse me, that shrinks the most will be on the inside. So it turns out in that picture on figure 17.6 that basically if you cool it down, the coil rotates itself more this way, causing the actual needle that's just physically attached to the end of the coil would just point at a lower temperature. And then if you increase the temperature, it's going to rotate the other way and pull off another one. Really, all you have to do is make one of those and then use something to measure the temperatures and then calibrate it by putting marks on it at specific places for wherever the needle pointed when it was at those specific temperatures. So it's a really ideal little tool. So that's pressure was one thing we could use as a scale to help us, or as a variable that could help us determine temperature. Another one we could do is, for instance, the resistance in a resistor, or the resistance of any material for that matter. And that's where a lot of them, a lot of the devices that you use in your house work by. For instance, I think I might have mentioned to you that our dryer once was burning clothes and stuff of that sort. And we literally had like a brown burn mark on the inside, and it would smell really, you could smell like a material was about to catch fire, and you could even touch the top, and it was hot to touch, like dangerously hot. So I knew something was up. I looked in it, and they actually had a diagram inside, and I could see that there was only 3 thermostats that it had, or 3 temperature related objects that would determine temperature. And those are like little safety switches that once it gets to a certain range, it makes the heater cut off, the dryer cut off. Uh, or can be a feedback system where it tells the heater to stop putting so much current to the heating element. Either way, I knew that at least one of those were bad, so it turned out they were like a couple bucks each. So I bought all of them and just replaced them all. And the dryer has been good for, I guess it's been about 3 or 4 years now. So that's a wonderful thing to do. I will warn you that when you go opening up electronic objects or even electric objects that are supposed to be simple, like a dryer or a washing machine, there's still some probability, even if you take the plug and pull it out of the light receptacle, there's still some chance that you're going to get electrocuted. Okay. So do this with caution or don't do it at all. Okay. It turns out there's certain electronic devices inside of electronic stuff that can retain voltage over a long period of time. So even though you unplug it, there could still be something at a very high voltage that can deliver a very high amperage, and it only takes about a milliamp to kill you. So the best way to do such a thing, if you actually have to go in one because it's a life or death sort of situation, is you go through with your multimeter or your voltmeter or something and check everywhere to see where voltage is. And then you can take, for instance, a wire connected with, let's say, an alligator clip, and plug that into the ground of your light receptacle, or connect it to the screw of your light receptacle, because that's supposed to be grounded unless you've got a really old one. And then you can go around with that alligator clip and touch everything. Uh, Obviously not using your fingers or whatever, but you'd actually connect the alligator clip to everything that you could possibly come in contact with, and that'll automatically ground things. That's the safest way you can do it if you're forced to do it. So, but other than that, let me see. Well, just about any variable you find that is either directly or indirectly, if it has a functional relationship between temperature, it doesn't matter what the functional relationship is. You can always build the device to use that functional relationship to tell you what the actual temperature is based on that variable. So I've mentioned to you pressure. You could also do volume. You could also do resistance. You could also do resistivity, which is slightly different than resistance. So there's a lot of different things. You can use also the actual thing that a thermometer is made of, or at least the thermometers that you probably were used to. Some of you are young enough now that you might not have ever used an alcohol or mercury thermometer, but alcohol or mercury thermometer is basically a piece of glass with a very narrow tube down the center and a pool at the bottom. And that pool can hold either mercury or some kind of alcohol, toluene, or something along those lines. And the volume expansion is what you're making use of there. It turns out that just about everything, if you increase the temperature, you increase its length, you increase its width, you increase its height, or more specifically, you increase its volume. So if you increase the temperature of this liquid, whether it be mercury or toluene, the total volume is going to increase. That's going to force the column of mercury or toluene or alcohol that's in the tube to go up higher, higher, and higher. So that's how that works. Any questions on that? All right, so I see no real other problems jumping out at me with regards to temperature that I didn't address. Your book does talk about a constant volume gas thermometer, and it shows one in figure 17.8. So by all means read that. And I will tell you, the more of your textbook you read, the better off you'll be, at least in the long run. Just be advised, sometimes you read a whole paragraph and it doesn't seem like anything stuck in your brain. But you'd be surprised where some of that stuff pops back up later. And not only that, if you can get yourself to read it twice or maybe even 3 times during a semester, you've got a much bigger chance of it sticking. Additionally, if you read it before I cover the material, You'd be surprised how much you get out of the lectures when I mention the same things that you read, but maybe mention them in a different way. That ability for you to have a little conversation sort of to yourself with yourself on what's being said and what you think is going to be said next versus what you think was going to be said, and so on and so forth. That makes you better learn the material. So, you know, ideally, my best case scenario for you guys is you read the material I'm going to cover before I cover it. Then I cover the material, and then you read it again. Usually I cover like a whole chapter during the summers. I usually cover a whole chapter in a day. So the ideal scenario would be you'd read a whole chapter before I cover it, but you might have to do that in small slices, because if you read a whole chapter, even if you make it through it, chances are you're not paying attention the whole time. So you need to find out, how long can I read before I lose my attention span? So do a little test on yourself. Set a stopwatch going, start reading the most boring section in the textbook that you can, and read along. And the first time you get some kind of thought that comes into your head, oh crap, I got to go take a shower. Oh crap, my meeting's in an hour or something like that. Anytime you have a distracting thought, just stop the timer and measure what that is. Don't be surprised if it's a minute. Don't be surprised if it's 45 seconds. Don't be surprised if it's 3 minutes. Okay. But what you're going to do is the next maybe 5 to 10 times you read, you're only going to read for that long. And then next time after the, 5 or 10 trials, maybe you increase it by 10%. And you read that 5 or 10 times, and then you increase it by 10%, and you read that 5 or 10 times, and you increase it by 10%. And only doing that will you get a better hold on it. And over time, you'll get much better. What any good college student ideally would be able to do is be able to read for, let's say, on the order of 2 to 3 hours straight without losing attention span, even if it's the most boring thing ever. Okay. Now, if you're under a stress situation or you're in the middle of a panic attack, forget it. You're not going to read anything. But other than that, that would be the holy grail of a college graduate, is to be able to read for 3 or 4 hours straight uh, without losing attention span. Now, I did, for instance, once, because I had to train myself to do this, because I told you I was a really poor student in high school. So I was a really poor student, and literally by the time I graduated high school, I only read 3 books, and like 2 of them were just stuff I shouldn't even read. It's just goofy stuff that I was interested in, and then the third one was one I was assigned by a history teacher. So I had a very weak system of reading, but over time I realized how to fix it, and I got to the point where one day I actually read a whole book in a single sitting. That took me about 6.5 hours, which is sad because the book wasn't that long. It was a Jack London book, White Thing. No, yeah, I think it was White Thing. But anyways, it's one of those type things. So yes, do this and don't feel bad about yourself. It's just, all of us go through this. So we all got to figure out sometimes. Some of us are lucky then that we've been immersed in reading since, we were 5 or 6 years old, but other ones not. So just do your best. Any questions on that? I know that's not physics related, but it's my soapbox stuff that might help you. All right. So the next thing I wanted to talk about is thermal equilibrium and the zeroth law of thermodynamics. So what I wanted to explain to you about thermal equilibrium is, let's imagine you have an army of gremlins, but these will be like magical gremlins. These will be itty bitty things that are like microscopic, like the size of a virus. And they can get down at the microscopic level and look and see atoms flowing back and forth and stuff like that. And they can see one atom from one object bumping into an atom of another object that's actually leaning against it, stuff like that. Okay, so if you had this army of gremlins and you had a block and another block and you put them right next to each other, what you'd see is if this object and this object were not in thermal equilibrium, what you'd see is maybe this one has atoms or molecules or both that have a higher random kinetic energy. And the atoms and molecules in this one that has the higher kinetic energy, when they get near the edge, they bump into the atoms and molecules of this one that have a lower kinetic energy. And that causes that particular atom or molecule that's been hit to increase its kinetic energy. Then that little atom runs off, or that molecule runs off and runs into other atoms until eventually the whole average of all the atoms and molecules is a little bit higher now, but not much. But over time, you watch that with these little army of gremlins, and what you'll see is that over time, the average kinetic energy moving forward, backwards, left, right, up, and down, that average kinetic energy of all those atoms and molecules for the one object and the other are now all of a sudden exactly the same. Now, they don't have to be identical atoms and molecules. So this one could have really big molecules that are heavy, but have very low speeds. And this one could have very small molecules that are light and have high speeds. The main thing is their kinetic energies, which is 1/2 mv squared. Those are actually equal. If that's the case, then what's going to happen at that point is, yeah, you're still going to have an atom from one object hitting another object and making it speed up, but you're going to have just as many of that happening as you're having it happen the other way, where the atom on this side is actually a little bit more energetic than the atom on this side, and therefore it speeds up the other one. So the net effect is that nothing's happening. Once you get to that point, because the average random kinetic energies of the molecules in both of the objects are the same, you're in what's called thermal equilibrium. And in the next chapter, we'll learn that the average random kinetic energy, at least associated with moving forward, backwards, left, right, and up and down, those three types of kinetic energy, when they're all averaged and equal each other, that is the very definition of having temperatures being equal. So it turns out that that average random kinetic energy going in, out, left, right, up, down, that for any substance is basically one multiplier away from being the temperature in Kelvin. So you literally only have to multiply a number by the kinetic energy and out pops the temperature in Kelvin. So what is thermal equilibrium? Thermal equilibrium is when two objects are in contact with each other some way, and the average random kinetic, or what we call translational kinetic energy of the one object and the other are both the same. And therefore that means the two temperatures are the same. So when temperature A equals temperature B, they're in thermal equilibrium. Now, that is what happens with thermal equilibrium. So we later realized that we hadn't really thought out the entire process. So we had to introduce, even though we had a first law of thermodynamics and a second law of thermodynamics, we had to go back and introduce something called the 0th law of thermodynamics, namely because we'd already used the number 1 and 2. What we mean by that is, let's imagine for a second that we have a cute Yoda rock. So here's a cute Yoda rock, baby Yoda. Okay, or I forgot his name now. Anyways, all right, let's have him in contact with him. Okay, if I find that Yoda and the glass clip are in thermal equilibrium, yay, we know that the temperature of the Yoda rock and the temperature of the glass holder are both the same. So temperature A, T sub A, is equal to temperature B, T sub B. Okay, because they're in thermal equilibrium. Now, if we take the Yoda rock and put it in contact with glass case carrier number 2, which we'll call part C, okay, and we find that our gremlins tell us, yeah, there's no energy being exchanged, then we know for a fact that Yoda is also in thermal equilibrium with C. So we now have A, which was in, here's the gray one, A was in thermal equilibrium with B, and now we find A is also in thermal equilibrium with C. So the 0th law of thermodynamics says that if A is in thermal equilibrium with B and A is in thermal equilibrium with C, then guess what? B and C are in thermal equilibrium with each other. So that's what the 0th law of thermodynamics is. The universe didn't have to work that completely rational way that you think shouldn't have ever been an option. So that's why we had to do it. The universe didn't have to be that way, but it turns out it is. So we, in retrospect, went back and put a 0th law of thermodynamics. Does anybody have a question on that? Okay. Remember, all this is being recorded, so you can go back and listen to what I said again, because obviously my words are just like gold falling down, you know. No, it's not all that, but still, if you doze off or something, you might need that. So that's the 0th law of thermodynamics, and your book states it: if two systems are in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. That's the way your book states the 0th law of thermodynamics. What I want to go into now will require some notes, and we're actually going into specifically thermal expansion. So what I am going to do is share my iPad screen with you guys. So I'm going to do share screen, iPhone, iPad, AirPlay, push share, and now I have to select screen mirroring on my iPad. That should come in. You'll see I've preloaded some stuff that I wanted to tell you guys just to save us a little time. Okay, so what might seem reasonable to you, hopefully, okay, is the following. We know, based on the atomic theory of matter, which, by the way, I did find that Feynman quote, so I'm going to put that up in our in somewhere on our Canvas page. I'll let you know when I do. But given what we found out about the atomic theory, we do understand that as temperature increases, the average random kinetic energy of the molecules are going to increase, and that's going to make the spacing between them in a solid be slightly larger. What I am suggesting that you might understand is, let's say I take a 1 foot long aluminum ruler and I take it out of a house in which the temperature was 10 degrees Celsius, so like 50 degrees. That'd be a really cold house. It's my heaven, really, to be honest with you. As a fat dude, I really appreciate a good 50 degrees Celsius temperature. It's excellent to me. Or excuse me, 10 degrees Celsius, which is about 50 degrees Fahrenheit. So let's imagine a 1 foot ruler is at 10 degrees Celsius, which is about 50 Fahrenheit. And then we're going to have another aluminum plank that's, let's say, 10 foot long. Okay, made out of the exact same aluminum, and it's even the same geometric size, except instead of being 1 foot, it's 10 feet long. Now, I take both of them outside at the same time, and I touch them exactly the same amount, and then I lay them on the ground and let them reach equilibrium with the outside, where it's, let's say, 30 Celsius, which would be god-awful 86 degrees hot, right? If I do that, okay, do you think that the change in length of the 1 foot long aluminum ruler would be the same as the change in length of the 10 foot long aluminum ruler? That's a lot of sentences. I'm going to restate it just in case someone didn't understand. I've taken a 1 foot ruler made out of aluminum and a 10 foot ruler made out of aluminum, both at equilibrium at 10 degrees Celsius, which is about 50 Fahrenheit. And I've taken them both outside where it's 86 degrees Fahrenheit or 30 degrees Celsius. And in doing so, I allowed them to reach equilibrium. And because the atomic theory of matter, both of those 1 foot and 10 foot aluminum pieces will increase their length. And I'm asking you, will their increase in length be the same? Do you expect, for instance, the 1 foot one, maybe it increases by 1/8 of an inch? Would you expect, therefore, that the 10 foot one would also increase by an 1/8 of an inch? Looks like the 10 foot will increase more, is what my chat is saying. Yes, that's absolutely the case. So, what I would tell you is that implies that the change in length, delta L, is directly proportional, which means thumbs up, is directly proportional to the initial length, L0. So that's what this box is saying up here, where I have delta L. This little fish symbol is what we use in physics to say proportional. So delta L is proportional to L0. Okay. Now, I also would ask you and see if you agree with me. Let's say I take two 10 foot rulers, or two, let's say two 1 foot ones to make it simple. Two 1 foot long aluminum rulers, both of which are at equilibrium at 10 degrees Celsius or 50 degrees Fahrenheit inside the house. And then I'm going to take them both outside and subject them to 30 degrees Celsius or 86 degree Fahrenheit weather until they reach equilibrium. Okay. Now that works fine. But let's say instead of doing that, let's say I take one of the 1 foot rulers and I subject it to 30 degrees Celsius. And then the other one I subject to 40 degrees Celsius, which would be another 18 degrees higher than 86. So that would be what, 104? So 104 degrees Celsius would be one, and the other one would be 86. Do you expect them to have the same change in length? No. Yes, so that's exactly right. You'd expect, in fact, that the one with the higher temperature change should have a higher change in length. So that tells us that delta L should also be proportional to delta T. And just for the record, in case y'all hadn't learned this from last semester, delta anything, notice I put a little empty box there just to represent anything you could put there, is equal to that anything final minus that anything initial. So in general, anyone that writes delta something and puts it in a paper, you have to automatically assume they mean final minus initial. If that's not what they mean, they have to make a point to tell you, because everybody in the physics community agrees to that. Okay. So that's what delta means, final minus initial. Now, you might also say, what if I did a 1 foot ruler and made of aluminum, and a 1 foot ruler made of, let's say, steel instead of aluminum? And this time I take them both from 10 degrees Celsius to both 30 degrees Celsius. Do you think they're necessarily going to change by the same amount of length? Thank you to the Sebastian and Ava, by the way. Yeah, they definitely should not change unless there's a freak of nature where two particular substances actually have the same property in this particular respect. And in fact, they don't. Okay, aluminum and steel have very different what we call rates of coefficients of expansion. So yes, you'd also say this change in length should be maybe proportional to some constant that represents the material you're using. Normally what you do is have that constant, and then you'd say to make it an equality, I have to put a constant in front of that, like you did in algebra. You said, V and T are directly related, so you'd write V is equal to some constant times T. Well, we could do this here. We could say delta L is equal to some constant times the number we put in there to represent the material times L0 times delta T. But in this particular case, we chose not to do that. We just let the K be absorbed into the constant for the material. So we get delta L is equal to alpha, which is the constant related to the material, times L0 times delta T. And the constant alpha is called the coefficient of linear expansion. Now, again, there's no reason the universe had to say that things are going to expand linearly, so that delta L is directly proportional to delta T. And in fact, they don't necessarily behave that way, but over a small enough temperature range, they do that very, very well. But if you wanted to go, say, from, like I did in these examples, from -10 to +40, say, and in this case, I actually went all the way down to -10 instead of +10. If you really wanted to do that large of a span, you probably couldn't use a single alpha for that material. You'd probably have to find an alpha for somewhere between -10 and 0, and do the conversion to find the new length at 0, and then find another alpha for something between 0 and 10, and use that to get you up to 10, and then find another one for something between 10 and 20, or 10 and 30, maybe the one for 20, and that would get you up to 30, and then you do it again for the 10. The net effect being that it's not really linear, but over a 5 to 10 Celsius degree range, that might be just fine. Okay, everybody follow that? All right, so I've taken some examples from the internet regarding coefficients of linear expansion. And for instance, the coefficient of linear expansion, hopefully y'all can figure out what the unit should be just by looking at this equation, because notice the L0 is a length and the delta L is a length. So the delta L and the L0 have to have the same units. And then the delta T, since the delta L and the L0 have the same units, those units more or less cancel out. And that means in order for it to be correct in terms of units, the alpha has to have the reciprocal units of the delta T. So you can see the unit should be Celsius degrees reciprocal, or the reciprocal of Celsius degrees. So for aluminum, it turns out the linear coefficient of expansion is 25 times 10 to the -6 reciprocal Celsius degrees, whereas for steel or iron, it's 12 times 10 to the -6 reciprocal Celsius degrees. Neatly and conveniently, the alpha, the coefficient of linear expansion for concrete, is also right about 12 times 10 to the -6 Celsius degrees reciprocal, or reciprocated. Does anybody know why that's important? For instance, I asked that in red letters. Why is it important that alpha Fe and alpha concrete are about the same? Anyone know that off the top of your head? So if you're thinking about going into engineering, one of the branches of engineering that are actually a couple of branches of engineering, civil engineering, mechanical engineering, and structural engineering, require you to use materials to hold things up. And it turns out there's one really awesome, there you go, rebarb reinforced concrete. Exactly. One of the most useful things that we use in the building industry is reinforced concrete. And reinforced concrete is made by basically putting steel rebar in tension. So you'd take like a 10-foot long chunk of rebar and you'd put it under tension where two sides of it, one end is being pulled one way and the other end is being pulled the other way. And then you form concrete around it. And it might be several pieces of rebar. The main thing is you're going to have some rebar in there. And then you allow it to dry. And only after it's completely dried and hardened perfectly, then you let the tension off the actual rebar. And what you have is a much stronger version of concrete and steel that's both stronger than steel and concrete, and is the reason that we can build really, really tall skyscrapers and stuff like that. That's a big part of it. So reinforced concrete's great, but guess what? If you actually do that and you do it, let's say, with aluminum and concrete, then the first time the weather changes for an appreciable period of time, the aluminum is going to reach equilibrium at the same time with the atmosphere at the same time, or roughly around the same time as the concrete does. And because the 25 is way bigger than the 12 that concrete has, that would mean the aluminum is going to expand so much that it breaks itself loose of the concrete and can't really provide as much support. It's sort of like the difference between having an Iron Man exoskeleton that's fully integrated versus just having the crappy skeletons that we have, which are sort of like, rebar with hunks of meat hanging on it. Okay. So yeah, that's a really good reason. All right. Now, another thing is that equation is really super useful, but often we want to know the final length as opposed to the change in length. So what I've done is taken the time to solve that expression for the final length. And you can see I'm doing that delta L equals alpha L0 delta T. I reinterpret the delta L as L minus L0. Remember, all deltas are final minus initial, so I'm calling the final L and the initial L0. Then I put the L0 on the other side, and then I see I have a common factor of L0. So this tells me L is equal to L0 times parenthesis 1 plus alpha times delta T. That particular form makes it really easy to see the units of alpha. So both of those equations are equivalent. That's the reason I took the time to show it to you. And you can use either one you want. And obviously, it's much more convenient to use the second version if you're trying to find out the final length. But if you're asked to find the change in length, then that first version is better. You can also see, by the way, aluminum, like I said, was 25 times 10 to the negative 6. Iron was 12 times 10 to the negative 6. Concrete was 12 times 10 to the negative 6. Glass actually ranges. For instance, Pyrex, the good stuff we use in labs, is 3 times 10 to the negative 6. And that's a really good thing, because I once tried to boil water in a pot that I thought was Pyrex, and it exploded. Luckily, I knew that was a possibility because I didn't know for sure this thing was Pyrex. So I kept my student away from it. And of course, I got the liquid blown all over me as opposed to him. Luckily, it wasn't that terribly hot. But yeah, Pyrex only has 3 times 10 to the negative 6, which is really good. Whereas ordinary glass has a coefficient of linear expansion of around 9 times 10 to the negative 6. So it expands 3 times quicker for a given temperature change. Liquid gas, meaning the stuff that you put in your car, assuming you don't have an electric car, is 950 times 10 to the negative 6. So you can see liquids expand by a lot more if that's the hallmark of the liquids. And I'm telling you, that is roughly the hallmark of liquids. The coefficient of expansion is way larger. You can see, for instance, the coefficient of linear expansion for water is 210 times 10 to the negative 6. Actually, let me double check that. That might be beta. I want to double check. Let's see. Yep, those are beta, by the way. Sorry about that. So these two right here, I should say, I'm going to zoom in. Now the gas is a liquid, so what I'm going to do is I'm going to erase the alpha and I'm going to write beta. Okay, and you're going to see why that's relevant in a second. Erase the alpha, and I call that beta. Whoa, my eraser was still on. I call that beta. And then air is going to be the same thing because that's a gas as opposed to a liquid. And we're talking about volume expansion, which is why I'm using the symbol beta now. Now, I haven't briefed you on this. I hinted towards it a little bit in previous class, but I'll tell you that you can also consider the expansion in two dimensions. So, for instance, if you had let's say a street sign is like this big rectangular or octagon shaped thing whose dimension other than the two dimensions is very small. In other words, the thickness of a street sign is very thin compared to its width and height. So that is in some sense more like a two-dimensional object. So it turns out when a solid expands, it expands in every dimension. Okay, that means the width expands, the length expands, the height expands. That's a common way for teachers to explain it. I'm going to address that in a second. So you can actually, going on the same arguments we use for the linear expansion, I can say that the change in alpha, or excuse me, the change in A, the surface area, is equal to a new constant, call it gamma, times the initial area, A0 times delta T. And it just happens to turn out that when you do two dimensions, the gamma is essentially twice as big as the alpha. You can up it to three dimensions, then you'd say delta V is equal to beta times V0 times delta T. And guess what? As nature would have it, it turns out that beta is essentially 3 times as big as alpha. So when I say, oh, beta for a gas is 950, that's not really comparing apples to apples when we compare that to 3 for glass or 12 for concrete. Really, I should divide it by 3 to compare, but you can still see it's a lot bigger. So gases, liquids expand way more than a solid does for a given temperature change, and then gas does even further still. Because you can still, if you see, even if I divided 950 by 3, I'm going to get 300 and what, 20 something. So 320 something is still a lot bigger than 12 or 25. And if you look at it for air, it's 3,400. Even if I divide that by 3, I'm still looking at around 1,130. So 1,130 is still way bigger than 3 or 12 or 25. Any questions on that? All right, so those are your equations, and these will be the equations, for instance, that are on the equation sheet, which you can download from your Canvas page, and you can laminate it if you want, because you're going to use it over and over again for your face-to-face tests, for your practice tests, and for your online tests. So feel free to print it out and whatnot. And if it's not there, I'll put it up, but I think I did already put it up. So let's go on to the next page where we can see some examples. So example 1, the steel platform for a certain suspension bridge is 300 meters long at 20.0 degrees Celsius. It may be subjected to temperatures as high as 40 degrees Celsius and as low as negative 31 degrees Celsius. What is the difference between the platform's longest and shortest length? Think about what you would do to ensure. Oh, that's supposed to be an E ensure, not I ensure. I don't like that at all. Ensure. Actually, now I'm thinking that might not be right either. I'm thinking of the ensure the drink, but either way, it's one of those. This isn't an English class. We're going to go with it. Okay, so think about what you would do to ensure that the platform is safe for drivers. So that's sort of the application side of this, is you want to think about such things, especially if you're considering going into mechanical, civil, or structural engineering. So let's just start off by working the problem. Okay, so solution. Normally, a lot of physics is learned just by starting off to learn exactly what symbols mean what, and reading the problems and associating each number they give you or imply with a specific symbol. So, for instance, they told us the platform for a suspension bridge is made of steel. So I know alpha should be alpha of steel, which is about 12 times 10 to the negative, why did I write a 2 there? 10 to the negative 6 reciprocal Celsius degrees. I also know that L0 is 300.0 meters. So that's pretty helpful. The steel platform for a certain suspension bridge is 300 meters long at 20 degrees Celsius. It may be subjected to 40 degrees Celsius and negative 31 degrees Celsius. So what I'm going to say is, at least sort of with part A, T is going to be let's start with T0. T0 is going to be 20.0 degrees Celsius, and then T is going to be 40.0 degrees Celsius. And then for part B, let's say T0 is equal to 20.0 degrees Celsius, and T final is going to be negative 300 or 31.0 degrees Celsius. In both cases, I want to know delta L is equal to question mark. And specifically, what I want to know is L at 40.0 degrees Celsius minus L at negative 31.0 degrees Celsius. That's what I really want to know. Okay, the delta L is something I'm going to have to calculate, and then I can use logic and reason to get from delta L to what they actually want. So does everybody understand what I wrote down and why I wrote it down the way I did? Anybody have any questions on that? Okay, so let's go ahead and do it. So first off, I don't need your help there, Cosmo. So what I'm going to do is I'm going to say delta L for part A, and notice I just called that part A. It's not supposed to necessarily be A. It didn't list that in the problem. So I'm just trying to do it to make sure we have some understanding of it. So delta L is supposed to be equal to, right here, I'll write the equation we're using just to remind us. Delta L is equal to alpha L0 delta T. So I'm going to say delta L is equal to 12 times 10 to the negative 6 reciprocal Celsius degrees. I'm going to multiply that by 300.0 meters, and then I'm going to multiply that by part A. I said it was going to go from 20 to 40, so I'm going to say 40.0 degrees Celsius minus 20.0 degrees Celsius, like that. And now I can just compute that. That's going to be 2 e to the negative 6 times 300 times 40 minus 20 is 20. So I'm going to say times 20. And that gives me 0.072. Now, if you notice, these Celsius degrees, once subtracted, become degrees, or these degrees Celsius is once subtracted become Celsius degrees. So clearly they cancel out with that guy. And the only units you have left are, in fact, the meter. So this is 0.072 meters, which is pretty small change compared to the 300 meters, right? But either way, we've got that now. Now let's look at part B, where part B is saying we're going to go from 20 to negative 31. So let's do that one. What we're going to have is delta L sub B is going to be 12 times 10 to the negative 6 Celsius degrees reciprocal. Well, that was just something that got worse when I tried to fix it. So going to say negative 6 like that times 300.0 meters times, now it's going to be negative 31.0 degrees Celsius minus 20.0 degrees Celsius. So in this case, it's going to be negative 31 minus 20, which is negative 51. So that's a much bigger deal. So I'll type in 12 e to the negative 6 times 300 times negative 51, and that gives me negative 0.0, or excuse me, negative 0.1836 meters. Now I actually put in the first case, I only had 2 sig figs because the 12 was limiting me. So basically, these 0.072 really is the full number of sig figs. In the second part, the same thing's true. So that means this 3 and the 6 are not sig figs. So I should underline them to keep that straight. So what this means is L at 40.0 degrees Celsius, that was what happened when it got up to 40, and it turned out to be only an increase of 0.072 meters. So I'm going to say that length is 300.072 meters. But I should remind you that in adding it to 300, significant digit rules suggest that the 7 and the 2 are not going to be significant. So I have to underline them there to keep that. And then remember, I'm actually trying to calculate this quantity right there. Okay, that L at 40 minus L at 310. So now I'm going to take and subtract from it what 300 minus 0.1836 is. So if I type that in, just to be careful with my arithmetic, 300 minus 0.1836, that gives me 299.8164. Now, in this case, neither the 6 nor the 4 are significant figures, nor is the 1, because the 300 was only covered to 1 decimal place. So that answer is 299.8 basically. So when I actually do the subtraction, I'm going to say 300.072 minus the previous answer, and that's going to give me 0.2556 meters, which is essentially 26 centimeters. But mind you, I only had 1 sig fig to the right of the decimal place. So basically, this 5, and the 6 were not sig figs. Okay, so I really should just call this 0.3 meters is the difference in length from the longest to the shortest. So 30 centimeters, which is pretty significant. 30 centimeters is not a small distance. For instance, you could divide it by 2.54 to find it in inches, and you get about 11.8 inches. So this is nearly a whole foot difference. So as I said, you want to think about what would you do to ensure this platform is safe for drivers, because if you butt them right up against each other, when they go to expand, they could actually crush each other and cause the concrete to break or bubble up or something like that. And then when they get really cold, they could spread apart so far that you have not a blum 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 expansion break, but a pothole, basically a 12-inch wide hole in the bridge. So if you look at the photo in your book for an expansion break, you'll see that one of the things that engineers often do is they'll take and make the end of the platform shaped like that, and then the other end of the platform would be shaped like that. So it can allow one piece to go inside of the other. You could account for like 6 inches of the 12 inches just by overlapping those two. And when they expand or contract, they would never leave a hole for the actual tire to fall in, that kind of stuff. So that's one of the many fixes. You also have to think about, are you going to allow them to actually move? So it almost like, imagine that the platform that comes up like this, and then the other platform that comes up like this. The fact of it being a suspension bridge means that a whole platform is held up by cables, and from one section that's cabled to the other end of the section that's cabled, you're going to have some kind of pier for it to stand on. So what you want to think about is how am I going to implement it such that it doesn't pull the pier over or break the pier or something like that. So we often do such designs by imagining that the platform is sitting on a wheel. And then you have to actually implement that from an engineering standpoint. How are we going to do that? Because you can't really just put a rubber wheel up there, because rubber actually dry rots and becomes quite unhealthy and unhelpful over many changes in temperature. Okay, so you do stuff equivalent to that, but maybe not exactly that. Any questions on that one? All right, so we're covering a lot of information there. I'm talking about it probably way more than I should, but I really want you to understand the concepts. So let me look back a second. It says, in general, us teachers often say that expansion of solids causes every dimension of the solid to increase with increasing temperature. What do you think this means regarding the diameter of a hole in a plate? So what I'm talking about here is you could imagine, for instance, a plate like this. And let's say it's actually a three-dimensional plate. So it's actually got a thickness associated with it as well. And it'd be like that. And this would look like this. And this would look like this. And this would look like this. So when I say every dimension is going to expand with increasing temperature, what I mean by that is this direction is going to expand. This direction it's going to expand, this direction it's going to expand, this direction it's going to expand, and this direction it's going to expand, as well as in this direction it's going to expand. So what does that say, for instance, for a hole that you actually had in that plate? If you had an actual hole in that plate, then it would look something like this, right? So does this dimension, let's actually not do that way. So in this case, does this dimension expand and this dimension expand and this dimension expand? That would suggest the hole gets bigger. Or does this dimension expand and this dimension expand and this dimension expand and this dimension expand? So that's a bit of a philosophical conundrum. I'm actually reading a chat right now. It says, so when they expand in construction, they don't expand at different rates. Oh yeah, gotcha. Yeah, you're answering my question about concrete. Good job, Ethan. So sorry I didn't see that till now. Now, if you look at this, the answer to the question is obtained by thinking about, let's take, for instance, a handicap no parking sign or something like that. It's really thin, so you don't have to think about the thickness. You can just think about it being two dimensions. Now, instead of actually punching a hole in it, let's just draw with a mechanical pencil, very sharp, a perfect circle on that sign. And then we heat it up to make it get hotter and hotter and hotter. I think you can see that the diameter of that drawn circle is going to get larger. Okay. Now, if you took and went just inside of that penciled line that makes a circle and did a little cutting and cut out that circular plate just inside of that circle, and you heated the plate with the hole in it, and you heated the plate that was the hole, you would definitely reach the conclusion that the plate that was the hole got larger. Does that make sense? And can you think of a good reason why, when the plate is put back in, when the whole plate is put back in the hole that you left, can you think of a good reason why all of a sudden that plate would get, that whole plate would get smaller? The whole shaped plate would get smaller? You can't, really. Okay. So that's the answer to it. Or if we want to defer to experiment, we have various things we use in the physics department. And one of the things we have is this little brass rod that sticks out of a handle and has a ring on it. And then another brass rod that sticks out of a handle has a sphere on it. And if you just hold them together at near the same temperature, basically the sphere will not go through the ring. But if you take, again, the spring and the ball, the rod, and the ring are all brass. If you take and heat up that brass ring, you can then fit the ball through it. So that shows you that the hole actually does increase in size, just like the piece of metal that used to be in there increased in size. So yeah, it behaves just like the piece of metal that would be in there. Okay. Any questions on that? Now I ask another question. How does water behave differently than most other substances? Has that been helpful in the past? So, what I mean by that, hopefully you got it from the reading, but I will make a little graph to make sense of what I'm talking about. So, if you make a plot for water of, let's say, volume of, I'm going to call this V for volume. So, this is the volume of 1.0 grams of water. Okay. If you actually do this, what you'll find is that if I put this to be 0 degrees Celsius, and then this to be 1, and this to be 2, and this to be 3, and this to be 4, and 5, so on and so forth. So this is all in degrees Celsius. What we discover happens with the volume is the volume actually gets, the volume actually gets quite small in here. So it comes down, 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 and reaches its minimum right here at 4 degrees Celsius, and then starts to climb back up. And in fact, it goes on like this. You could also make a plot of density versus temperature instead of volume versus temperature. And remember, density is equal to, if in case you forget this, I'll give you the neat little thing that high school teachers do. They draw a little heart, and then they draw a line through it to remind them that density is mass over volume, because the heart with a line through it looks like an M over a V. So you can see that density and volume are inversely related. So in this case, what you're going to find out is, let's say this is 0 degrees Celsius. Let's say this is 1, 2, 3, 4, 5, 6, something like that. What you'll see here is that the density is a maximum at 4 degrees Celsius, and it in fact gets smaller and smaller and smaller at 0 degrees Celsius, and then it gets smaller and smaller and smaller for all the other temperatures like that. Okay. So what that tells us is, let's take water that's at 6 degrees Celsius, right at the surface of the water. This might be the Great Lakes, which you know is quite windy. Because the temperature gets really, really cold, the water's gotten down to 6 degrees Celsius, and then all of a sudden it makes the air above the water makes the water get even colder. So the water is going to actually go from, on the surface, is going to go from 6 degrees Celsius to 5 degrees Celsius. And if we look at that graph, this graph is telling us that from 6 degrees Celsius to 5 degrees Celsius, the density actually went up. So that water that went from 6 degrees Celsius to 5 degrees Celsius then sinks down. And of course, a higher density, or excuse me, a lower density water, which might be the 6 degrees Celsius stuff, will come up to replace it. And then that will get cold and reach, say, 5 degrees Celsius and sink down. And then another 6 degrees surface water will come up, and that will shrink down. And then all of that can go over again until the whole water's reached 5 degrees. Then it'll go from 5 degrees to 4 degrees, and the same thing will happen again, happen again, happen again. But this time at 4 degrees, that's the maximum density. So that water will sink all the way to the bottom. And then the air on the top will be hitting the 4 degrees Celsius. But now the water is 4 degrees Celsius from top to bottom. So that top surface now is going to go from 4 degrees Celsius to 3 degrees Celsius. That's actually less dense than the 4, so it'll stay right on top. And then the air will get so cold that it'll actually bring that 3 degrees Celsius down to 2 degrees Celsius, but that's still less dense. So it'll push the 3 degrees Celsius stuff down and stay on top at 2 degrees Celsius. And then that'll get colder and that'll push the 2 degrees Celsius stuff down because it's now at 1 degree Celsius. So that'll stay on top. But then that water up at the top will go from 1 degree Celsius to 0 degrees Celsius and start to sink down because that's again less dense, or excuse me, that is again, less dense. So that'll stay on top in this case. Sorry about that. I was mixing it up. But the main thing is what you'll ultimately have is the very bottom will stay at 4 degrees Celsius because that's the most dense part of water. When water's at 4 degrees Celsius, it's at its most dense. So it'll be at the bottom. And what's happened is slowly you've gotten everything above it colder still until some part is actually zero. And that zero part is, of course, less dense than the 1 degree part. So it will tend to sink down. But then the 1 degree part will start to reach zero. And then that'll try to sink down further. So you end up slowly building up a big chunk of ice on top. That ice is actually acting like a good insulator, preventing further degradation or further decrease in temperature from occurring. So if we had the most catastrophic ice age in the history of mankind, or even in the history of the planet, it's pretty we're pretty confident that the very bottom of that body of water would still be at a 4 degrees Celsius and be liquid so that actual sea or water life would live. So, in that sense, it has been helpful and it's allowed, in some sense, us to live through ice ages, or I say us, I mean all living creatures on planet Earth. Which at the time might have been only water going creatures, all of those could actually survive an extreme ice age. So, yeah, in that sense, it's been helpful. Any questions on that? All right. And finally, why does running hot water over the lid of a tight pickle jar lid help? Okay. So, what I'm going to refer you to is when I talked about the coefficients of expansion, you see that, let's say the typical lid of a pickle jar is like steel. Okay. It could be tin or some other crap or aluminum. Aluminum's a little too expensive. Copper's too expensive. Probably it'd be steel or tin. And steel and tin are all around 12, 14, 15, 16 times 10 to the negative 6. But if you compare that to glass, which is the jar, you can see that glass, Pyrex or ordinary, still has a smaller coefficient of linear expansion than does the steel. So when we actually heat up the lid by running hot water over it, we're heating up the lid, and to some extent, the glass is going to be heated up, but that doesn't matter because the glass is not going to expand its diameter in such a way that it overcompensates for the amount that the metal has expanded. So the metal diameter of the lid, that metal lid will actually expand greater than the glass does and therefore make it loose so you can still loosen it. Now, if it's not too wet, then you can get enough grip and you can pop it open. Any questions on that? All right. Well, it's 6:47. I haven't given you guys a break yet. So what I'm going to do is go ahead and give you let's say let's say an 8 minute break. So come back at 6:53, or excuse me, 6:55. So 6:55, we'll come back. So that's about 8 minutes from now. Go ahead and take 10 minutes. That's cool. Okay. I'll start back up. I'll be here in case anybody has any questions, but I just want you to get a break in case anybody needs to go to the restroom or anything like that, or you just need to let your brain cool off. My clock says it's 6:51. I'm planning on allowing you guys to stay away till 6:57. So you got 6 more minutes. Got about 4 more minutes. Oh, 3 more minutes, everyone. Nobody's asked any questions, but feel free to type them or ask them if you have them.
When is the first test?
Oh, good point. That is one thing I don't have off the top of my head. I actually, what will help you, there's going to be a first test on chapter 17 and 18. So next week I should finish chapter 18. So I suspect what will happen is I will make it available, the online test, uh, Monday, not this coming Monday, because that's a day that you don't have class, by the way. But the following Monday, I'll probably make the first online test available. And usually when that happens, I usually give you the whole week to do it. So it'll probably be due like Sunday night, not this coming Sunday, but the following Sunday. The first face-to-face test, I'm going to refer you to your lab instructor. She has her schedule where your lab time has an open day off. That's going to be the first face-to-face test because it happens in your actual lab. So if you look at your schedule from your lab instructor, that'll tell you when the first face-to-face test is. Now, I did explain this to you, but just in case you didn't hear it, or I didn't explain it well enough, or since you don't have the syllabus up there right now, the online tests are open book, open notes, open internet searches, and everything. Usually, I have the time set that you only have a few, less than a minute per question. So if you have to look up more than one of the questions, you're probably going to run out of time. Uh, that being said, I've been altering how I do that lately, but I'll just say that in general, if you have to look up more than one, you probably didn't learn the material very well, so you need to definitely address it after the fact, but still you can get as good a grade as you want. Okay, so that's the way the online tests work. The face-to-face tests, if they're done at home, which sometimes I can allow, you'd have to do it with a lockdown browser and a mirror. So you actually have to have a good sized mirror where we can set everything up with you and a webcam and that sort of stuff. But other than that, it's just going to be a face-to-face test that's administered in your lab, and you're not allowed to use anything but the equation sheet that I made, and of course a calculator and blank paper. So yeah, so a week from Monday, tests will come available for an online test that should cover chapter 17 and 18, and you should probably have until Sunday to do it. During the summer, it's hard to give you a whole week, so there might be times where you're going to have two online tests due on the same Sunday. Like one will come available on Monday, I'm still going to give you till Sunday, and the other one's going to come available on Wednesday, and you still have until Sunday to do it. That might happen, but hopefully not. And oh, also the other thing with the online tests is I always give you at least three chances, and I only take your highest score. All right, it's 6:57, so I'm going to go ahead and get started. Anybody else have any questions on anything we just covered, or on the questions that someone asked about the tests? Okay, so you'll notice, and you can remember you can download these from my Google Docs, my Google Drive. So feel free to do so. You can also take a screenshot of it, but I've basically written down in blue the answers that I gave you are an extremely short version of it. So hopefully that will be helpful too. In addition to actually hearing it, which I suspect you understood when I said it, but in case you didn't, I wanted to go ahead and put down exactly what my answers were to some extent. So anybody have any questions on that, feel free to ask or email me. Or like I said, if you do email me and you don't hear back from me within one school day, as explained in the syllabus, which you don't have, uh, then that's the time where you want to send it to me via text, because it's my responsibility to get back to you within one class period. For instance, what one class day means is, for instance, if you email me tomorrow morning at 12:01 a.m., in other words, just after midnight, so it's now Friday, but literally it's only 1 minute into Friday. If you send me an email at that time, since we have off Monday, that means I don't have to reply to you until 11:59 or by 11:59 on Tuesday. Every other day, it's just, if you send me an email at 12:01 on Monday, I have to reply to you by 11:59 on Tuesday. Okay. All right. So now that I've shown you this, hopefully anybody that needed to take screenshots or anything like that, they've been able to. This is the density of H2O plotted on the vertical axis. I didn't actually specify that. And this is temperature in degrees Celsius. I also forgot to specify that, so I wanted to make sure I wrote that in there. I've shown all those little arrows. I've written the blue lines to make sense of it. So let me go ahead and show you what the next page is, and it's another example. So example 2, the 100.0 liter tank, steel gas tank of a truck is filled up when the gas and the tank are at 10 degrees Celsius. How much gas will overflow if the temperature reaches 40.0 degrees Celsius? Okay. So what we're picturing here is a big steel gas tank, like on a Mack truck, or at least like a F-350 or a Chevy for those people that like Chevys and Rams, a 3500 or something. So it's a good sized tank basically, but I wanted to stick to gas because I don't have the coefficient of linear expansion for diesel fuel. I do have the coefficient of linear expansion for gas. Okay, so that's what we're going to do. I'm going to go ahead and write that the solution is right here. And I'm going to try to make some sense about how to work this. So the thing we're going to use is we're clearly talking about a whole volume expansion. So that means we're going to use delta V is equal to, oops, not alpha, but beta times V0 times delta T. And beta is generally 3 times alpha. In this case, we can actually use 3 times alpha for the steel, but we can't use it for the gas because we're only given beta in that case. So that's some of the information our solution is going to require. But just like I just finished explaining to you, remember I asked you, what do you think a hole in a plate is going to do when the temperature causes the plate to expand? We learned that the hole is going to behave just like the piece of metal that used to fill the hole. So the hole is going to expand too. So when we're talking about a steel gas tank, what we can imagine is a rectangular chunk of steel. Uh, and then think about the hole in it, or think about the tank as a rectangular solid chunk of steel that has all of it gutted out such that the volume inside is 100 liters. That 100 liter of air is going to expand and contract just like 100 liter cube of steel, and that's the way we're going to treat it. Okay. So what's going to happen is the gas is going to expand because it's also going from 10 degrees Celsius to 48 degrees Celsius. And what we saw is that liquids expand way more rapidly than solids. Remember, it was like 950 versus 12 or 25 or something like that. In this case, we are talking about steel, so we know that alpha is equal to, this is alpha for steel, is equal to 12 times 10 to the negative 6 Celsius degree reciprocal. But we're actually talking about the volume of steel. So that means that beta for iron, which is equal to about 3 times alpha for iron or steel, is in fact about 36 times 10 to the negative 6 Celsius reciprocal Celsius degrees. Okay, so that's what we're going to use for that. And then we're also going to make use of gas, which I think was 950, but let me double check. Yes, gas, beta for gas was 950. So I also have to make use of the fact that beta for gas is equal to 950 times 10 to the negative 6 reciprocal Celsius degrees. Now I'm going to go on the assumption that 950 has 3 sig figs. Now I'm not one that cares that much about sig figs, but when you're actually doing problems on MyLab and mastering, even though I've got it set where it's not supposed to pay attention to sig figs, the actual answers are often done, and I say often, I don't even say most of the time, are done with proper significant digit rules. Uh, in fact, that's sort of how I got the little bit of quote unquote fame that I did get as a person that writes web pages for physics textbooks and astronomy and mathematics textbooks. I got somewhat famous for being really meticulous about my solutions. And the Pearson group put me in something called the group called Aztec, which was the absolute zero tolerance for errors club, specifically because probably out of 150 problems, maybe somewhere between 80 and 120 had sig fig errors, and I caught all of them and told them all about them. That trend did not cause them to change their mind. That trend just pointed them out that they did it wrong. And in fact, authors has continued to do it. So you'll find a lot of sig fig errors in MyLab and mastering. But the ones that are done correctly will actually, by you knowing proper sig fig rules, will actually allow you to get exactly the right answer. And that feels really good when you get the right answer to the right number of sig figs. The biggest problem that I discovered was when you add or subtract, you often make your answer come out to 1 sig fig. And that's what the authors were trying to avoid, the authors of the problems and the authors of the pages and the authors of the solutions manuals and all that stuff. So they weren't really doing it to be jerks. It was just a matter of they hadn't thought it out, or the author hadn't thought out the problem well enough to make sure you never come up with 1 sig fig answer. So, all right, now I've got all that information. I also have that T0. Oops, I should continue writing this in red since it's a solution. I also have that T0 is going to be 10.0 degrees Celsius, and I have T final, which we're just going to call T, is 40.0 degrees Celsius. And finally, I have V0 is actually equal to 100.0 liters. Notice that's 4 sig figs. You'll notice that I do a lot of problems like the ones that are done in the textbook, but I almost always don't allow numbers like 100 to be up there. I'll change it to 100.0, or I don't allow numbers like 20 to be there. I'll call it 20.0. Okay. So again, I'm going to treat the gas as one thing, and that's going to expand, but that's not how much gas is going to overflow, because guess what? The imaginary steel block that represents the air inside of the tank, that's going to expand as well. So what I'm going to do is I'm going to take the expansion of the gas minus the expansion of the air tank, okay? And that will give me the amount of overflow, because basically the expansion of the steel that represents the air inside of the tank, that's going to mean a decrease in the overflow, because the tank's going to expand to accommodate some of that gas. So that's how I'm going to work it. Does everybody understand my reasoning there? Okay. Looks like they're getting it. So I'm going to say overflow. So delta V overflow. I'm also going to call that delta V OF. Okay. That's going to be delta V gas minus delta V tank. So that's the equation that I just made based on the argument and the reason and logic that I just gave you. So hopefully that better helps you understand. So what I'm going to first do is calculate the delta V of the gas, and the delta V of the gas by the formula beta V0 delta T should be beta for gas is 950 times 10 to the negative 6 reciprocal Celsius degrees times the V0, which is 100.0 liters. Notice whatever unit you put in for the volume is the unit that comes out of it. And the temperature change is going to be 40.0 degrees Celsius minus 10.0 degrees Celsius. So I'm going to get basically 30.0, that's 3 sig figs, times 100.0, which is 4 sig figs. So I'm limited to 3 sig figs so far, times 950 e to the negative 6, which is also 3 sig figs. So my answer should come out in 3 sig figs, and what I get is 2.85. And I'll just put a 0 on there and do liters, and I underline the 0 to let you know that that's not a sig fig. Okay. Now I'm going to calculate delta V for the tank. Now remember that that's basically acting like a steel block that's 100 liters in volume. So I'm going to say it's 3 times 12, which is 36. So it's going to be 36 times 10 to the negative 6 reciprocal Celsius degrees times 100.0 liters. So that's 2 sig figs times 4 sig figs. So that limits me to 2 sig figs times 40.0 degrees Celsius minus 10.0 degrees Celsius which obviously is going to give me 30.0 again, but that's 3 sig figs. So I'm limited to 2 sig figs in this case. So I'm going to say 36 e to the negative 6 times 100 times 30. And that gives me 0.108 liters. And this only has 2 sig figs, so the 8 is not significant. That means, according to our rational hypothesis that we made, or a rational argument that we made, the actual overflow will be 2.85 liters minus 0.108 liters. So this, by the way, 3 dots in a triangle means therefore. Okay. Therefore, delta V overflow is equal to 2.850 liters minus 0.108 liters, which equals 2.85 minus, that gives me 2.742 liters. Notice the sig figs dictate that we only have 2 decimal places. So the answer is going to be 2.74 liters will overflow. Any questions on that? So that's a little more complex problem of linear expansion. This happens to be a linear expansion in volume, so that's a little more complex. Plus, we had to think out the reasons of what the gas is going to do versus what the tank's going to do, and realize that we had to subtract one from the other as opposed to add one to the other or something. So that is a little more complicated of a problem. Does anybody have any questions on that? Okay, the next section is section 17.5, which is thermal stresses. I'm actually skipping that, but I don't know why I wrote 2 L's there. That was kind of a crazy thing. I'm actually skipping this, but I want to give you some information that I've found helpful, just so you'll know it. And you can see this, you can see what I'm telling you in chapter 12. Okay. So what I've learned is there's these quantities called modulus or moduli of elasticity, Young's modulus, bulk modulus, shear modulus, all these different moduli. That's the plural of modulus. So moduli. And what I've learned is the best way to think of a modulus is stress over strain. So I'm going to give you that information. So modulus, and this means no matter what modulus you're using, that could be Young's modulus, that could be the bulk modulus, that could be the shear modulus. They're all defined as, whoops, they're all defined as stress over strain. Okay. If you go into engineering, especially mechanical, civil, or structural engineering, maybe even some branches of electrical engineering, you need to know your moduli and you need to know how to use them. So this is why I'm taking that. What I want to show you is that the word stress has RESS in it. And I want to show you that the word pressure also has the RESS in it. That's what I use to remember what stress and what strain, because I know that pressure is equal to force divided by area. Okay, that normally means force divided by area perpendicular to the force. And that helps you realize, oh, when they talk about the stresses, that's the thing that has to do with force. So a shear force would be, for instance, F over L, where L is actually parallel to the force. or F over delta L or something weird like that. In this case, it's just going to be F over L. The strain, on the other hand, is something geometric. So I will remind you that this is, ooh, actually, I wanted to do that in a different color so it would stand out. This is geometric. So it means like delta V over V or delta L over L or something like that. That's what strain is. So all your moduli are stress over strain. Your stress is always going to be something dealing with a force, and your strain is always going to be something dealing with a change to geometry. Okay, so I'll say geometric. I think that's close enough. The reason why I say that is your book uses in the example that it's working under thermal stresses, which I highly recommend you read and read the example, because this is really a cool calculation you can do. What I want you to look at is they give you this equation: delta L is equal to 1 over E. And of course, E is a modulus. And in fact, the E here, I just want to double check, make sure I'm reading it properly. Yeah, the E is the Young's modulus. I used to use Y for that. That's why I wanted to make sure. So the E is the Young's modulus. And what you get is F over A times L0. So in fact, this is often delta L or delta V over V0 or delta L over L0. So you can see that delta L over L0 would be the stress, or excuse me, would be the strain, and the F over A would be the stress. And delta L over L0 equals the strain. So that's all they're using in this equation, is they're using that the Young's modulus E is F over A divided by delta L over L0. Okay. And from that, they're able to calculate what pressure is put on an adjacent concrete slab when the temperature changes from a low temperature to a high temperature. So that's a really powerful calculation. You can actually find out what the force of a slab of concrete pressing against another slab of concrete is as a result of the temperature changing from 10 degrees Celsius to 40 degrees Celsius. So that's a really important thing. But the main thing I wanted you guys to know is that you can find out about moduluses in chapter 12 of this book. I'm probably going to make up a homework set for chapter 12 that you can do as extra credit if you want. And then you'll remember that modulus is stress over strain, and hopefully that'll help you. You're going to have a lot of time to learn about moduluses and stuff like that as you go into, if you're choosing engineering, as you go into your branch of engineering. But I'll tell you, for instance, when I did structural engineering, we would have to calculate the bending moment of a beam, and we'd have to calculate the shear moment of a beam, and then we would have to take that maximum bending moment and divide it by a modulus to find out what cross-sectional area of the beam was needed to actually make sure it wouldn't succumb to that force. And by doing that, we could look up in a table and say, oh, I needed this much area of the beam. And then I'd look at a 2x10, 2x8, 2x12, 2x16, or whatever I wanted. And once I got an area large enough, then I knew that that beam would work. And I do the same thing with the shear, but then I'd use the shear modulus as opposed to the other modulus I was using. And that would allow me to actually do it. Of course, the modulus depended on what kind of wood or steel I was using. So you'd actually have to look up whether you wanted the modulus for spruce, pine, fir, or the modulus for southern yellow pine or oak or whatever. So anyways, that's the relevance of my engineering experience that I'm trying to share with you to some extent. So anybody have any questions on that? I actually think that kind of stuff's really interesting. You also would do things like, you'd marry a piece of steel to two pieces of wood, because steel is not very good if you load it the way it wasn't intended to be loaded. It just, folds like taffy or something like that. So it's not very fun or very helpful to work. But steel is very strong in the dimension that it's meant to be strong. So you can take what's called a flitch plate, which is a big chunk of steel that maybe is an eighth of an inch, a quarter of an inch, or a half inch thick. And you could sandwich that between, for instance, a 2x10 sitting on top of a 2x12. And you could take a 2x10, a 2x12, and then span the whole distance so you leave it long enough, and then you secure that to a flitch plate that is maybe a quarter inch thick chunk of steel, and then you put another 2x10 and another 2x12 on the other side, and then you bolt it enough that it all acts like one piece. And then that would be a header that could hold open a garage door, for instance, or maybe the opening under a beach cottage so that a car could drive under it. So all that stuff was very interesting to me. Hopefully you'll find something like that in your area of major that you'll find interesting. So now we're going to go into the ideal gas law, which starts in section 17.6. Your book talks about equations of state. The ideal gas law, for instance, is an equation of state. There's another equation of state that you might be familiar with. It's called van der Waals equation. I'm a scuba diver and I've had some, courses in scuba diving and mixed gas diving, stuff like that. So you might find it interesting to learn that when you actually go to mix up a trimix of gas, or if you try to use heliox or nitrox, those are some of the gases that you can breathe other than just regular air. It's not enough to use the ideal gas law. You sometimes find enough deviation that the ideal gas law is not good enough, and you have to use van der Waals equation. So that's kind of interesting as a real life application. Specifically, the problem is when you try to make heliox or nitrox. Nitrox, basically air is supposed to be 80% nitrogen and 20% oxygen. But you only need, your body only absorbs about 4% of the air and of the oxygen, or I should say 4% of the air you breathe is oxygen that you actually absorb. So you've got way more than enough oxygen in that, and oxygen actually becomes toxic at certain depths. So you got to be very careful and not put too much oxygen. But nitrogen gives you what's called nitrogen narcosis, the rapture of the deep, which is a euphoric feeling. I thought rapture is a bad thing when I was a kid, so I didn't really understand that rapture of the deep meant that you get euphoric and happy. It's basically a drunkenness. So you get a little drunk from nitrogen. So what you can do if you want to go down to depths that aren't too deep is you can use nitrox. If you want to say go to 75 feet or something like that, you can use nitrox 1, which has, instead of, let's say, 80% nitrogen, maybe it drops down to 70% nitrogen and 30% oxygen. And that keeps you from feeling as drunk, and it actually allows you some safety because you're now behaving more rationally because you're not drunk from the nitrogen. So that's why you would breathe that. In some cases, for instance, when we opened up the Monitor off the coast of Cape Hatteras, the Monitor is a really deep dive. It's about 235 feet off the coast of North Carolina. And Gary Gentile came down from New Jersey. Gary Gentile is the one that dove the Andrea Dora for the first time, which is also a very deep dive, but a very deep and dark dive. But he came down to dive the Monitor and used our dive shop. And I got to read his book and all that cool stuff. But one of the guys that went with him was a Navy diver and a Coast Guard diver, and he actually used heliox. So he would actually mix helium in there to get rid of some of the nitrogen and without increasing the oxygen, because if you go to 230 feet with 20% oxygen, you can't stay there very long. And if you go too much deeper, you could actually die from oxygen toxicity. So he would use a mixture of helium, nitrogen, and oxygen, or in his case, I think he actually just used heliox, which is just helium and oxygen. And that allowed him no narcosis whatsoever. And this dude was awesome. Like you're out in the middle of the ocean. The ocean's 230 some feet deep where you're at. You're several miles off the coast. And it's kind of scary when you jump in the water and go down and the water's really clear, which it is because that's in the Gulf Stream as opposed to the Labrador Current. The water's pretty clear, not like Caribbean clear, but still very, very clear. And you can tell because if a diver goes down and he's 80 feet in front of you, you can see him really clearly. whereas normally we have 5 to 10 foot visibility on the Outer Banks as the most often event. So in his case, he didn't necessarily. He told me that he actually did this specifically because he didn't like the creepy feeling you had as you go down. You have about 80 feet of visibility. So when you get to about 100 feet, you know that the visibility is really clear, but you look up and you can't see the boat, and you look down and you can't see the bottom, and you look to the left and the right and you can't see anything. It's all kind of creepy. You just see blueness, and it's almost like you've gone blind and can only see blue. So instead of getting worrying about that little fear, this Nazi crazy person, I'm being funny about the Nazi thing, this just intense individual would literally grab the anchor and jump in with it. And the anchor would pull him down lightning fast to 235 feet, and then he'd lock the anchor into some part of the shipwreck that wouldn't harm it and would keep the boat still, and then he would dive. And he drew the most beautiful drawings of the monitor because he wasn't narc. At 235 feet, you are punch drunk, ugly, stupid acting with regular air. So, and not only that, you only get like 2 minutes there, and then you still have to do stage decompressions. His problem was when you use helium stays in your blood even longer than does oxygen and nitrogen. So his decompression time was even longer. So he would usually get on the order of 15 to 20 minutes on the bottom and spend 6 hours coming back up. So you had to wear like a dry suit, because if you spend 6 hours even in 75-degree water, you're going to get hypothermic. So he actually had to do much longer for you using heliox. All right, that's enough about that. So yeah, there's an equation of state. The ideal gas law is one. Van der Waals equation is another. There's actually more. In fact, not too long ago, in the last couple decades, we actually computed an equation of state for a rubber band. And that's actually now an example in many statistical mechanics textbooks. And it's really cool because you can now work out a lot of details about a rubber band, which isn't that important, but just to have a accurate equation of state that's accurate at many levels is pretty impressive. We'll also say that the things that describe a condition are called the state variables. For instance, for a gas in a container, the state variables are pressure, volume, temperature, and the quantity of the gas, which could be measured by the mass or the number of moles or the number of atoms. Those are all possible quantities that you use as state variables. And we also just analyze basically equilibrium states. We don't really have good physics for non-equilibrium states. We're building that, but it's a very complex, difficult area of physics research. So we only treat state variables at equilibrium. So initially, what came up were some very specific laws. For instance, the scuba diver's law, which is Boyle's law. So Boyle's law is really what I would say is consistent with the true nature of the word law. If you take any gas and you say the mass slash number of moles slash number of atoms equals a constant, and the temperature is equal to a constant, then Boyle's law says that volume is inversely proportional to pressure. That's the scuba diver's law, because the scuba diver's rule is never hold your breath, never hold your breath, never hold your breath. That being the case, because if you actually, for instance, go to a depth of 100 feet, the pressure at 100 feet is basically 4 atmospheres total. And if you go from 100 feet to or from 99 feet to 66 feet, you go from 4 atmospheres total to 3 atmospheres total. And that's not that quick of a change. For instance, you're going from 4 to 3, that's only a change of 25%. Whereas if you go from 33 feet to 1 feet, you go from 2 atmospheres to 1 atmosphere, that's a 50% change. So the actual most dangerous area is 0 to 33 feet. But still, that change in pressure could be a problem. So when you go from 99 feet to 66 feet, that's a decrease in pressure of a whole atmosphere of pressure. And that decrease in pressure means the volume of your lung is going to get bigger. And therefore, if you're holding your breath, your lung is going to blow up, and it's going to give you what's called an arterial gas embolism, where you could basically die. You're going to start having seizures and various other things. You could also get the bends from other things, but the main thing is this is volume and pressure are inversely related. As long as the total amount of gas, which can be measured in mass, or moles, which is what the lowercase n is, or atoms, which is what the uppercase n is. So this is number of moles, and this is number of atoms slash molecules. So if you keep the amount of gas of the T a constant, every time you do it, if you increase the pressure, the volume will decrease. If you increase it more, the volume will decrease again. Also, if you decrease the pressure, the volume will increase. If you decrease it again, the volume. So in that sense, it truly is a law. You're never going to find a violation of that. Okay, so that's Boyle's law. Oops, I should probably write that in blue. And then there's another one. This can also be written, for instance, that P times V equals a constant. But again, it's important that you know this stuff has to be true. Okay, P versus V is only a constant if that other stuff's true. There's another law called Charles's law, and Charles's law says that pressure and temperature are directly related, if I remember correctly. Let me double check out. Temperature also affects the volume of a gas, but a quantitative relationship between V and T was not found until more than a century after Boyle. Okay, yeah, that's it. So we also find Charles's law. That's a Charles. I know it doesn't necessarily look like it, so let me try to fix that as best I can. So that's Charles's law. And Charles's law says if you go on the assumption that m slash n equals a constant, then volume and temperature have a distinct relationship, but you also have to keep P equal to a constant. And what we find is volume is directly related to temperature. So another way of writing that is you could say volume over temperature equals a constant. But again, you can't say that in isolation. You have to have this true. So I'm going to say and. That's Charles's law. And then there's also one called the Gay-Lussac law. And the Gay-Lussac law, I think it's two S's. Let me double check. Yes, it is two S's. Lussac, Gay-Lussac law. That says that pressure is directly related to temperature. Okay. But again, that's not in isolation. In this case, you have to have the mass or the number of moles or the number of atoms or molecules is equal to a constant. And you have to have that the volume is equal to a constant. So again, this is a extra part of that has to be true. And in this case, you could actually say that that means pressure over temperature equals a constant. Again, these three are actual laws, what I would be acceptable, what I consider acceptable uses of the word law. So that's what those are. If you put all those together, what you'd find that is that P and V is equal or proportional to a constant, right? So because P times V equals a constant, but you do find that T is directly related to temperature and V is directly related to temperature. So you might as well say P times V is directly proportional to T. And you might even reach the conclusion that if I take at a fixed temperature and a fixed volume, if I take more atoms or molecules or mass of gas and pump it into that collection of glass, I think you'd expect the temperature to go, or excuse me, the pressure to go up. So you could say that that's directly proportional to M, but you could also say Rn R capital N. Okay. So this turns out to be the ideal gas law. And the way you convert a proportional to an equals, as we know before, is you add a constant. So ultimately, this leads to pressure times volume equals nRT. This is one of the versions of the ideal gas law. And I want to add the caveat that this is the number of moles of the gas. This has to be in Kelvin. Oops. And this is the ideal gas constant. Now, I will tell you, if you're going into engineering, there's going to be something called engineering thermodynamics. And in that world, they have an ideal gas constant for each individual substance. So you can look up the ideal gas constant for hydrogen, and it's going to be different than the gas constant for helium, and that's going to be different from the gas constant for water, which is going to be different from the gas constant for carbon monoxide, which is going to be different from carbon dioxide, and so on and so forth. So just to make some sense of that, I will remind you that in a typical chemistry class, you learn that you can find N by taking the mass and dividing it by M, the molecular weight, which is what you get from the periodic table. So when we say in engineering thermodynamics, what they would say is PV equals M times R times T, and this R is our R divided by the molecular weight. Okay. So what I'm going to tell you, for instance, is what is the ideal gas constant, or the actual value. Let me not put that in purple, because that purple was supposed to be a sidebar about engineering thermodynamics. So what I'm going to say is R equals the ideal gas constant that we use in physics and chemistry. And sometimes they use more consistently, they use a different value. In physics, we almost always use 8.314 joules per mole Kelvin for the ideal gas constant. And chemistry, in chemistry and in physics, but in chemistry, they more often use this one, which is 1.99. In this case, it's calories per mole Kelvin. But they also use 0.0821, and that one is in liters times atmospheres per mole Kelvin. So, oops. Let me actually write this on a different line, because I'm going to have a hard time fitting the units in. So it's also 0.0821. And this is liters times atmospheres over mole times Kelvin. Okay, so that's our three ideal gas constants. Anybody have any questions on that? So you can see we're going to use often pressure. Pressure is going to be in Pascal. So I'm going to put this here. 1 Pascal is defined to be 1 Newton per square meter. Okay, so that's how these units work out. But that's not the only thing you can put it in. You can also put it in units of atmospheres. as you can see. And I think that's pretty much it. Yeah, with the constants I gave you, that's pretty much what it could be. This one should be in meters cubed or in liters, just like the pressure can be in pascals, newtons per square meter, or atmospheres. The volume can be in cubic meters, in which case you're going to use the 8.314 or the 1.99, or it can be in liters, in which case you're going to use the 0.0821. Does that make sense? All right, so let me give you also the T can't be gauge pressure. Must be absolute pressure. Okay, so that's all the rules associated with the ideal gas law. There is one more rule that I should point out. It usually doesn't come up in physics, but it definitely comes up in chemistry. So if you're actually capturing a gas over a liquid, like often happens with certain experiments you do, like if you submerge, let's say, seaweed underwater and then you expose it to light, what will happen is the light will bombard the seaweed, and the seaweed, being a plant, is going to take the light and the oxygen and turn it into carbon dioxide. That carbon dioxide, or excuse me, yes, it's the other way around. It's going to take the carbon dioxide and the light and turn it into oxygen. So it'll produce oxygen over top of the water in the test tube that you have it in. And that gas above the water not only has oxygen in it, it has water vapor. So you actually have to look up what the pressure, the vapor pressure of water is, to at whatever conditions you're dealing with that gas, and include that in the P. So that's the one step about the ideal gas law that we often don't use it in physics in general, but you more frequently do it in chemistry. So I just wanted to make sure you know that. So I will do a couple of problems with this, and then I'll let you guys go. We only got about 8 minutes, so let's look at an example. And I think this is like example 3, but who knows? Yeah, that's example 3. So we're going to say, let's say an ideal gas is in a sphere. Oops, that's too small lettering. Is in a sphere at 27.0 degrees Celsius and 1.00 atmospheres of pressure. I'll give you some conversions on that as well. If you don't allow any gas to escape, if no gas escapes while while T, excuse me, while T goes from 27.0 degrees Celsius to, let's say, 130 degrees Celsius, and I'm going to put a 0 there and a extra decimal point, so you know how I do that. 130.0 degrees Celsius and 27.0 degrees Celsius. What I'd want to know is what will be the new pressure. Now, there's a couple of ways you could do this. What I'm going to do is I'm going to write down the solution, and I'm going to use the ideal gas law straight up just to make sense of it. The ideal gas law says PV equals nRT. And in this case, we're using atmospheres of pressure, which you can see lends itself to the 0.0821. So I'm going to say R is equal to 0.0821 liters times atmospheres times mole or per mole times Kelvin. 27 is T1 equals 27.0 degrees Celsius, which is 273 Kelvin plus 27.0. So you can see that's actually going to be 300.0 Kelvin. Okay. And then T2 is going to be 127. So 273 Kelvin plus 127. That's going to be 400 Kelvin. I'll say 400.0 Kelvin. So what I can do is I can say PV equals nRT gives me that the pressure was, I didn't write that first, right? 1 atmosphere. So P1 equals 1.00 ATMs. P2 is equal to question mark. So P1's V1. All right, P1 V1 is equal to N1 R times T1. Now, the volume didn't change, so there's no reason for the V to be subscripted, and no gas escape, so the N1, the N doesn't need to be subscripted, and of course the R is a constant, so that doesn't need to be subscripted at all. So what we can glean from that is that P1 times, let's say P1, well, I'll just leave it like that. So P1 is equal to NR over V times T1. Okay. And then I can say P2 V2 equals N2R T2. Again, the volume doesn't change because it's a sphere. The gas isn't let out, so the N2 stays a constant. So in this case, I can say P2 is equal to NR over V times T2. And you see the NR and V are the same, so I can write NR over V is equal to P1 over T1, and that's equal to P2 over T2. So I can just take that middle guy out and say P2 over T2 is equal to P1 over T1. So now I can say P2 is actually equal to T2 over T1 times P1. So I actually use the full ideal gas law, but believe it or not, this is a version that we actually introduce. And the more general case is P1 V1 over T1 is equal to P2 V2 over T2. That is completely equivalent to the ideal gas law as long as N equals a constant. So for this one, what I'm going to do is I'm going to say P2, which is what we're asked for, is 400 Kelvin over 300 Kelvin times 1.00 atmospheres. This way, I don't even have to use the ideal gas constant. So this is going to be 1.33 atmospheres is the pressure. That's it. Any question on that one? All right. So a typical thing that happens, and this is lightning fast, everybody should know the volume of 1 mole at STP. So I'm going to say example 4, what is the volume of 1.00 moles of an ideal gas at STP? So I'm just going to write the answer down here. What we want to know is PV equals nRT, and I want to know the volume. So V is equal to nRT over P. And this is where I'm going to remind you that the standard temperature and pressure is a temperature of 273 Kelvin, i.e. 0 Celsius, and the standard temperature, like I said, is 273 Kelvin, and the pressure is 1 atmosphere. So with that in mind, what I want to use is the 8.314. So I'm going to say, I'm going to say 1.00 moles times 8.314 joules per mole Kelvin times 273 Kelvin divided by 1. Actually, I'm going to move that over a little bit, say 1.00 atmospheres, but 1.00 atmosphere is 1.01 times 10 to the fifth Pascal per atmosphere. So that's the conversion factor you guys need. And when I do this, I'll say V is equal to, and this is the last part. Oops, I can barely see stuff. 8.314 times 273 divided by 1.01 e to the fifth gives me 0.0224, or, and notice that unit comes out in cubic meters. And in fact, 1 cubic meter is well, 1 liter is 1,000 cubic centimeters. So I can actually convert that to liters by a factor of 1,000. So that's going to be actually 22.4. Oh, crap. 22.4 liters. So that's just a common number that people state all the time. So it's something we sort of expect our engineers and physicists and chemists to know. So that's the last problem. You guys are free to go. I'll wait for the last person to leave in case anybody has any questions, but thank you for coming. Have a great weekend. Remember, Monday you're off. Chapter 18, I'm going to push that due date back, so don't pay any attention to that due date, but definitely get chapter 17 done. If you have any questions, you can email me. If I don't reply, go ahead and send me a text. In fact, there's almost no probability for me to actually answer an email over the 4-day weekend. So you might just want to go ahead and send me a text if you have any questions on how to do that homework, and I'm fine with that. Have a good weekend, everybody. Thank you.
Professor Younger, I only had one question about a homework question.
Okay.
It's the chapter 17 homework problem 17.8.
Okay. Can you read that to me or something?
Oh yeah, it's a concrete highway is built of slabs 14 meters long and then parentheses 20 degrees Celsius.
Okay.
Uh, how wide should the expansion cracks between the slabs be at 15 degrees Celsius to prevent buckling if the range of temperature is negative 30 degrees Celsius to 48 degrees Celsius?
Gotcha. So that sounds almost like exactly like the example I just did. Let me pull it up right quick. That's basically, yeah, this one, where you basically, I had 20 degrees Celsius, which is what they were doing, but you're saying a range is from -10 to +30. Is that right? Or +40 or something?
Negative 30 to positive 48.
Okay, so yeah, you do these same calculations as you see right here in the solution, and that'll give you the longest and the shortest that the beam could be, or that the slab could be. And then you've got to remember that both sides are going to expand. So when the temperature gets really hot, both sides of the thing should just barely touch each other on full expansion. So what you really want the distance between them to be is the distance between, or excuse me, the total expansion that it has at that highest temperature, whatever that was, times 2 basically. So if it expanded from 20 to whatever the highest temperature was, if it expanded by, let's say 25 centimeters, then the gap should be 50 centimeters, because what you want them to do is ideally they just barely come to touch each other at the highest temperature.
Okay, I see. So I think the part that's tricking me up is it says that the explicit length at 14 meters is 20 degrees Celsius. And then it says at 15 degrees Celsius, how wide should the cracks be? So the only thing the range really dictates is like how large the crack will be to begin with, I guess.
Yeah, so you want to think like, hey, they planned this ahead. They knew the highest temperature ever to happen was this. So I'm going to take the slab and convert it from 20 degrees Celsius to the highest temperature, see what that change in length is, and then imagine the two slabs being twice that distance apart.
Okay, I see.
Yeah, and then you can see what the length will be when it's at negative 15, that lowest temperature, and basically that's going to pull back some amount from the 20 amount, so you'd actually now have the separation between them being basically that twice the distance at the highest temperature plus twice the distance at the lowest temperature. So the change from 20 to negative 15 times 2 added to the distance apart when they're longest, that should give you the whole answer.
Yeah, I see.
Does that
That
make
makes
sense?
so much more sense. Yeah.
Yeah, it's kind of hard to work through it. It took me a little bit to figure that out myself, but yeah, that should do it.
Thank you so much.
No problem. Does that help? All right. Well, have a good one,
I
sir.
also have a homework question.
Okay, go for it, Ethan.
It's chapter 17, homework 3, the pressure cooker.
Mm-hmm. What's it telling you on that one? I don't have them memorized. I don't have them right in front of me.
Oh, okay.
Smart
If an
one.
otherwise empty pressure cooker is filled with air at room temperature and then placed on the hot stove, what would be the magnitude of the net force on the lid when the air inside had been heated to 120 C? Assume that the temperature of the air outside is 20 C, room temperature. And that the area of the pressure cooker lid is A, and then take atmospheric pressure to be P sub A.
Gotcha.
I'm just having trouble taking between the ideal gas law and conveying that to like pressure and
Yeah.
like the
That's
area.
okay. You probably haven't covered fluid mechanics or something like that yet, and that's where you start to learn about pressure. So what you're going to do with that one is you're going to use the ideal gas law to figure out basically what the pressure is at. I think it said 20 C and then 120 C.
Yes.
Okay, so you can find out what the pressure is at 20 C, and then by using PV equals nRT. Uh, but they probably didn't give you the volume, did they?
Uh, I do not see the volume now.
Okay. So the main thing is PV equals nRT. So the pressure at 20 would be N, which should be the same for both of them, times R, which should be the same in both temperatures, over V, which should be the same at both temperatures. So NR and V are going to stay the same. And then times T1. So what you're seeing is P1 over T1 is going
So
to
it's
be
just the same P over T equals P over T
exactly.
before and after the heating.
Yep. And then,
Okay.
uh, so you're going to solve it just like the last one I showed you, and that'll get you the pressure at the end. Now, in order for you to understand that, the pressure is going to come out depending on which R value you use. It should come out in pascals, which is the same thing as newtons per square meter. So if you take the pressure in P2 and you multiply that by the area and make sure the area is converted to square meters, then that'll give you the number of newtons that it pushes up on the lid. The
So
atmosphere,
multiply P2 times the area of the
yeah.
lid.
But then the atmosphere is helping you. So atmospheric pressure, which is 1.01 times 10 to the fifth Pascal, if you multiply that by the area, that's the amount of force that's keeping it down, in addition to its weight, but they probably told you to ignore that.
So multiply P2 by the area and the atmospheric pressure.
No, multiply P2 by atmospheric pressure, and then subtract from it the atmosphere, or excuse me, P2 times the area of the lid minus atmospheric pressure times the area of the lid. That'll give you the total force that's pushing the lid up.
Okay.
Because the
Okay, that makes
atmosphere is
sense.
actually helping keeping it closed.
Yeah, yeah, it makes sense. It says net force to be F sub 120. Is that just mean 120 newtons?
Yeah.
Okay. All right. Cool. That's all I had. Thank you.
All right, no problem. Hope that helps.
Yep. Bye.
And feel free to send me photographs of the problems with the answers if you actually have a question for me. It helps not only seeing the question, but seeing the answer choices, because sometimes it's a matter of choosing the best answer as opposed to the right answer, because there might be several right answers, but only one best answer.
Okay. Yeah, this one's just a number, so I don't think
Yeah.
there's a choice, but I
Yeah.
have seen, multiple choice other places.
Yep. All right. Have a
All
good
right.
one.
Bye. Thank you.
You're welcome. See ya. All right. Well, looks like everybody's left. Have a good evening. Bye bye.